Om Shri Sai Ram. Welcome back to the 8th session of this chapter, Motion in a Straight Line. In this chapter, in this session, we will be talking about the equations of motion, which is the heart of this chapter. Until now, what we have discussed? We have discussed about displacement, distance, speed, velocity and acceleration and these terms, right? So, in these all terms we have discussed and understood, and now we will try to figure out how these terms are connected to each other in the motion, in the straight line motion, in the rectilinear motion. If you are given displacement, time and acceleration, how can you find the velocity? So, these all kinds of equations we will be studying in this session, alright. So, let us get started. So, kinematic equation for uniformly accelerated motion, alright. It is the uniformly accelerated motion. What do you mean by uniformly accelerated motion? That means the change in velocity is same for equal intervals of time. Okay. For example, if the velocity is changing 1 meter per second square, 1 meter per second, if the velocity is changing 1 meter per second per 1 second, that is called as a uniformly accelerated motion. If it keeps on changing, for example, the velocity in the first second, if it is 1 meter per second, in the second second, after 1 second, if its velocity is increasing, if the acceleration is increasing or decreasing, then what does it mean? The change of velocity is increasing or decreasing. What does that mean? It is non-uniformly accelerated motion, alright. So, for your information, what we call as rate of change of displacement? Velocity. What do we call as rate of change of velocity? Acceleration. There is another term we call the rate of change of acceleration. The rate of change of acceleration is called as a jerk. Jerk. Okay. It is nothing but rate of change of acceleration. And rate of change of jerk is called as a jounce. Okay. These are all the terms in the physical world we do not have that relevance, but mathematically the rate of change of acceleration we call as a jerk, and rate of change of jerk we call as a jounce. Rate of change of jerk. If it is changing, then from jerk will go to jounce. Okay. Now we will be only considering about the rate of change of velocity, that is acceleration. So, let us get started. Let us see how the particle is moving, how the object is moving. The object is uniformly accelerating, that means the slope is constant and it has some initial velocity, it has some final velocity. So, it started from some initial velocity at t equal to 0, and as the time is increasing, it gained the velocity because acceleration is positive. It is gaining some velocity and it reached this point where the final velocity is v. So, let us have these terms. Displacement will denote as x, time taken is t, from here to here time taken is t, initial velocity is v naught, final velocity at the point C is what? V naught, v, acceleration which it is having, which it is moving is a. So, these are all the initial conditions we know, not initial conditions, these are all the things that is being happened in the motion. It took time t to change its velocity from v to v naught, that means it is having some acceleration a. So, everything is denoted here. Now, using this, let us find the relation between this x, t, v naught, v and a. So, how do we find out? First thing, let us see a, let us only concentrate on a. If you concentrate, what do you mean by a? A is nothing but change in velocity by time, right? So, using that we can derive the first equation. So, before that, let us see the three equations. Final velocity is v equal to v naught plus at, this is our first equation. Second equation gives you the relation between the displacement, acceleration and time. First equation gives you the relation between the velocity and acceleration. Third gives you the relation between final velocity, initial velocity and acceleration, and also displacement. Acceleration, displacement and velocity relation, displacement time and acceleration relation, and also velocity acceleration relation. Depending on the conditions, you can use any of these 3 equations. Alright. So, before taking them for granted, let us derive it. I hope you have already derived in your 9th class. Let us once again let us derive it with a fresh approach. So, this is our graph. So, let this be O, A, C, D. Here also the let us give a come here as this point as F. All right. Let us derive V equal to V naught plus AT. So, this is our first equation. You know, acceleration is nothing but rate of change of velocity, right? What is this acceleration? Acceleration is nothing but slope. Slope is what? dV by dt, right? Change in velocity for the corresponding change in time. So, this much velocity changed for this much amount of time, right? The particle started here, went there. So, it changed this much velocity by how much time? It took this much time. Let this be t. Let this magnitude be t. All right. So, here t2 becomes t, t1 becomes 0. Here v2 becomes v, v1 becomes v0, because v0 is your initial velocity, that is v1, v2 is your final velocity, that is v, right. So, let us rewrite in this notation. So, A is equal to v minus v naught, right. This is the change in y by change in x, change in time. Acceleration is nothing but change of velocity, but by the time it took to change from v naught, it took t time to change from v naught to v. So, that is the ratio. So, rearrange this term. So, what it gets? Take this t this side. So, AT becomes v minus v naught. So, just I took t this side. So, what from here? V is equal to v naught plus AT. So, you can see the interesting thing here. Here it is having some initial velocity. This is also final velocity. Can you see this mathematically? Is it not a arithmetic progression? Right? You have a starting term and you have a progression. Second term, third term, fourth term. T is what? Nothing but the velocity in first second. If you want the final velocity after the 1 second, you put 1. You want the final velocity after 2 seconds, put 2. That means it is giving you the first term, second term, third term, fourth term. What is A is? A is nothing but the common difference there. Alright. So, you can relate, you can analyze this equation in that manner. So, basically we have proven that this is our first equation by taking the acceleration, definition of the acceleration. Alright. So, from here we have arrived here, and then final velocity is equal to initial velocity plus A into t, acceleration into t. Alright. So, this is the first equation. Now, let us see the second, let us derive the second equation. Alright. Where is our graph? This is our graph, and this is the point, let it be F. So, we need to find the displacement here. So, we have which graph? Velocity time graph. From velocity time graph, how can we find the displacement? We can find the displacement by calculating the area covered under the curve, right. This is the curve, right. This is the curve. The particle has moved from B to C. This is the curve. The area under this curve will give you the displacement. That is what we have studied, right. So, velocity into time is nothing but the area under this curve. Let us find the area under this curve, then we can get the displacement, right. This is as simple as that. Let us go. So A is V minus V naught by T, V minus V naught is equal to AT, right. So what is V minus V naught here? You can see what is V minus V naught. This distance is V naught, right, and this distance is what? V, right. This distance is V from here to here, origin. Now what will be this distance? This distance will be what? This distance minus this distance, the remaining distance is this. So that is V minus V naught, right. CD is V minus V naught. Now V minus V naught is equivalent to what? AT, right, because A is V minus V naught by T, A is nothing but the slope, right. Here what is the change in Y? Change in, if the slope is given to you, what is the change in Y here? Change in Y is nothing but the corresponding change in X into the slope. What is the slope? A. So acceleration, from this equation we got this V minus V naught equal to AT. We can use this term instead of this. That is the reason we are showing here. So OA is equal to OA is equal to BD. So these two are same, BD equal to T. So that means this is the T, okay, this point is T. OB is equal to V naught. So this is V naught, we already know, because this is the magnitude, this is the point V naught. So of course this will be V naught, alright. OB is equal to also AD, right. Now you can see CD is equal to BF. So let it be F as I told you, okay, this point be F. So CD is equal to BF, right, that is equal to OF minus OB. OF this, OF is this total is what? V, right, this total is V, this total is V and this is V naught. So the total value minus this value gives you V minus V naught. That V minus V naught here we have told you that is 80. So this becomes 80, this length, alright. So displacement X, displacement under this curve is equal to what? Area of this trapezium, okay, two parallel sides, you have a height. So this is area of trapezium, right. You can find the area of trapezium directly, or otherwise you can break into two parts. You can see this as a one rectangle, OBDA as one rectangle, and you can see BCD as a triangle. So area of a rectangle, area of a triangle, calculate them separately and then add them. Then what happens? You can get the area of OACB, the trapezium. Alright. So let us see. So area of OADB, this rectangle, plus area of the triangle BCD. Alright. So it is nothing but side. What is the area of triangle? It is a side into side, OB into OA, right. This is the area of rectangle. The area of triangle is what? Half into base OA, half into base into height. Height is CD. This is the height. This is the base. Alright. So this is the area of the triangle. Now you can easily just substitute the values now. What is OA? OA is nothing but T. OB is nothing but V naught. That gives you V naught T plus area of triangle BDC, half into T into, because this is the base, half into base into height. Height is nothing but CD. CD is nothing but V minus V naught. But V minus V naught we already know that we can write as AT, right? V minus V naught we can write as AT. Now just multiply them. X is equal to V naught plus half AT square. So this is our second equation of motion. Alright, where we have calculated the displacement. Now using the two equations we can easily calculate the third one. So let us derive v square is equal to v naught square plus 2ax. V naught is initial velocity, v is final velocity, a is acceleration, and x is the displacement that took in the time period t. If the t is not given, when it is starting from velocity v naught and changing v, how much displacement it covered. So it is basically the relation between the initial final velocities and displacement. Alright. So from equation 1 you already know v is equal to v naught plus at, we have already derived. Now from this, how can we write the t? We can write the t as v minus v naught by a, right? Using this, just what we have done, take the v naught this side, v minus v naught, the coefficient of a when it goes on this side, what happens? It divides. Alright. So in other words, you can say divide on the both sides with a, so it becomes t equal to v minus v naught by a. Alright. So we need to use this t. So from second equation we already know x is equal to v naught t plus half at square. This we have already derived, and we know this t, how the t in terms of velocity and acceleration. Basically what this is saying, this is the relation between initial velocity, final velocity and displacement, right? So we need to eliminate the t term from here, from this equation. So if you want to eliminate the t term from here in the terms of v and acceleration, how can you write t? Use the first equation, get the t in terms of v and v naught, initial velocity and final velocity, and then plug in the t here. So what we will get? Substitute t equal to v minus v naught here, then you will get v naught t, this is v naught into t which we got here, plus half into a, again t square. So v minus v naught by a whole square. So if you further simplify this, so it becomes like this, okay, v into v naught by a minus v naught square by a plus a by 2, plus you can carry on, it is a basic simplification. When you open this, you can see this term and this term cancels out, right? You are remaining with this term. So you have minus v naught square by a plus v naught square by 2a. So you can, these two can add up, right? These two can add up to gives rise to what? To give rise to v square minus v naught square by 2a. Alright. When these two will add up, what happens? Minus 1 plus 1 by 2. Minus, if you take v naught square by a as common, that will be minus 1 plus 1 by 2, that gives you minus 1 by 2. That is what it is written here. So it is v square minus v naught square by 2a. So that gives you v square is equal to v naught square plus 2ax. Here you need to know that x is the amount of displacement when the particle is changed, when the object is changing its velocity from v naught to v. If the object is already having some displacement at v naught, if the object is already having the some displacement at v naught, then or otherwise at t equal to 0, then we need to consider that as well. This is the net displacement, x is the net displacement when the object is changing its velocity from v naught to v. That means you can also write this as v equal to v naught square plus 2a into x minus x naught. Okay. So this will be your net displacement. In our case, the starting position we took as an origin. Okay. Then we made it as 0. That's why it became 2ax. If it initially had some displacement, then you need to consider that. Alright. Okay. So these are the equations of motion in our what we have already solved in the class 9, but in this chapter we have already discussed about the concept of calculus, right? So why not we we derive these equations using the calculus method, right? Let us derive the equations of motion using calculus method, it will be very interesting. Okay. So, let us suppose an object moves in a straight line, alright. So, these are equations of motion in a straight line, with uniform acceleration a. It is moving with a uniform acceleration a. So, the initial velocity on the object is u at time t equal to 0, and v is its final velocity of the time interval t. Okay. After time interval t, that means from 0 to t, it is traveling, it is changing its velocity from u to v, alright. So, first equation let us calculate velocity time relation. We already know acceleration is nothing but dv by dt we have. So, right. So, acceleration is dv by dt, where dv is the change in velocity in the time dt. So, this is the amount of change in velocity in the time interval dt, alright. So, take dt on this side. So, dv is equal to a dt. I took this dt this side. So, dv is equal to a dt, right. So, now what we do? We integrate on both sides, alright. So, how do we integrate? See, here dv is there, our equation was dv is equal to a dt, right. So, what we are doing here? We are having dv is equal to a dt, right. Now, we are integrating on both sides. When you are integrating on both sides, we need to see the limits of these two values. As dv is the small value that is increasing, that is changing from u to v. We are accumulating those values from u to v. Then t is the value, it starts from 0 and goes to t. Here you can see at t equal to 0, the value of v is, what is the value of v? It is starting with the velocity u, right. At time t equal to 0, it is having the initial velocity u. At upper limit of time t is, it is having, when it is reaching when the particle is reaching some distance at the time t, it is having the velocity v. So, at time t equal to 0, it is having u, at time t equal to t, it is attaining the velocity v, right. So, when we take the appropriate limits for these two quantities and then integrate. So, this is the definite integral. So, between these values we need to know how the velocity is changing when the acceleration is given. Okay. So, let us see. So, you already know integral of dv is what? V. Integral of dx is x. So, v, how the v is, from where to where we need to calculate the v? From u to v. Okay. That is equal to integral of t is nothing but what? That is also t, where the t is ranging from 0 to t. So, final limit minus initial limit. So, it becomes a into t minus 0. So, what does it become? V minus u, upper limit minus lower limit. So, it becomes v minus u is equal to at, that is equal to v equal to u plus at. So, from here you can write. So, if you take this, so upper limit minus lower limit, it is in the function of v only. So, v minus u, which implies v minus u is equal to at. So, from here we take the u on the other side, v equal to u plus at, alright. So, in the vector form, how can you write? These are all the vectors, right? Acceleration is a vector, initial velocity is a vector, final velocity is also a vector, okay. So, this can be written as in the vector form, v is equal to u plus at. So, this vector into scalar, so there is no dot product here. Now, let us calculate the distance time relation. So, in the same way, let us suppose an object moves in a straight line with a uniform acceleration a, at any instant time t, the change in position of object in time interval dt is ds. So, at any instant the change in position of the particle, when it is moving with the acceleration a, at any instance when the change in the time interval, it is having dt, the change in position will be ds. So then the instantaneous velocity of the object is given by v is equal to ds by dt. This is the instantaneous velocity. As the time is increased by dt, the corresponding displacement change in position it is having is ds, that is your instantaneous velocity. So in the same way what we have done for the acceleration, velocity and time, a is equal to what, dv by dt, then what dv we wrote as a dt. In the same way ds we are writing as v dt. So v is equal to ds by dt, ds is equal to v dt. We already know what is the final velocity, we already know from the first equation, v is equal to what, v is equal to u plus at, right. So this u plus at substitute here, this v is there now, so instead of v you write u plus at. So what it becomes, ds is nothing but u dt plus at dt. Okay, if you expand you will get that. Now what you will do, integrating both sides with appropriate limits. So the displacement is starting from 0 to ranging to s, at t equal to 0 it is at 0, when t it reaches t it is having a displacement of s. So integral of 0 to s ds is equal to u, we are integrating over time, velocity and what we are already, this is constant, initial velocity is not changing, it started with some initial velocity, acceleration is constant, it is not changing. What is changing, that how the time is changing, that is what we are integrating, how this function is changing with respect to time. So integral of dt here, again integral of t dt. So all the t terms we are integrating with as the displacement change in position is increasing. So we already know ds is nothing but, integral of ds is nothing but s, this we can also write as s, that means s minus 0, because lower limit is 0, that is why we wrote as s, that is equal to dt. Here also we can write this as u into t minus 0, that is the reason it is only ut. Okay. Here at dt, what is integral of x dx, we already know, that is this is x power 1 plus 1 by 1 plus 1, that gives you x power x square by 2, right. In the same way you can write, you can see it is t dt in terms of t, so it will boil down to t square by 2, x, like it is x square by 2, it is t square by 2. What is upper limit and lower limit? Upper limit is t, it started from time t equal to 0. So when you substitute that, what happens, you will get this result. Alright. So from the calculus method also you are getting this. You can think once, just go back, we integrated it, just go back, that means you differentiate it again with respect to time. What it gives, ds by dt will give you what, v, right, ds by dt will give you the instantaneous velocity v at that point of time. So d by dt of ut will give you what, u, d by dt of half at square will give you what, if you calculate you will get 80. If you d by dt of this function, if you do d by dt of this function, you will get the first function, first equation. So this is how they two are related, we need to understand that. Okay. So now you can see s equal to ut plus half at square, it came. So if you want to write in the vector form, s is equal to ut plus half at square. So all t is nothing but a scalar, it is just a magnitude, is having a magnitude, so there is no dot product here. So this is the vector form. Now let us solve for the third equation, velocity displacement relation. So equal to dv by dt. Now here small mathematical manipulation we do, we multiply and divide by ds. Okay, why we do, you will get to know. Now a equal to dv by dt you already know, just to this multiply and divide by ds. So does it make any change? It does not make any change. You are multiplying by same thing and dividing by same thing. That means multiplying by 1. If you multiply by 1, it does not have any change. But mathematically we are doing this, but physically they have some importance. That is why we are doing this mathematical manipulation. Alright. So this quantity we already know. After doing mathematical manipulation, ds by dt quantity we know, that is v. What is remaining? dv by ds. Let us play with that. So ds by dt is what? Rate of change of displacement, that is v. That means here this two, you just see these two. So what happens here? You just bring this ds this side, ads. What is remaining? Only this term is remaining, v dv, right? So our mathematical manipulation helped us to arrive at this equation, alright, because we want in terms of what? In terms of velocity, displacement, acceleration. So all displacement, velocity and acceleration. Okay. So we took out all the dt terms here. So our aim is to make sure the t term is not there. To make sure the t term is not there, we made ds, we multiply by ds and divided by ds. So when we made this, when we know ds by dt is v, we eliminated this dt term using v. So we are remained with only v terms and what? Displacement term and acceleration. So using this we can easily calculate the relation now. So integrating on both sides with the appropriate terms. So how the ds will change? It started from initial position 0 to some change in position s. How the v changes? It changes from u to v. It started from the initial velocity u and changed it to v, right? So this is the appropriate limits we put. Now integrating on both sides within the conditions, we get what? A, integral from 0 to s ds is equal to integral of v dv from where u to v. Okay. So we get this value, integral of ds, we already seen it is as. So v dv, like t dt, we got t square by 2. What is the range of it from v to u? So 2as is equal to v square minus u square, or v square minus u square is equal to 2as. Here you can see in the last when we derived conventionally, I have told you that this is the change in displacement. ds is the change in displacement when v is ranging from u to v. v is changing from u to v. If I have a initial displacement as s1, for example s1, then it becomes what? It becomes 2a s minus s1. See, upper limit minus lower limit 2s. Because I have taken 0 here, it became s. Alright, this is the net change in displacement. Alright. So in the vector form, now you already have this is v is a vector. Vector is multiplied by itself. So you can see the dot product here. A is a vector, s is a vector, u is a vector, v is a vector. So v square can also be written as v dot v. A dot product of two vectors is what? A scalar. Scalar will be square of this, because the angle between these two vectors is 0. Cos 0 is nothing but 1. So this is the magnitude. This is in the vector form. This is the scalar form. This is in the vector form. Of course, this will give you the scalar form because of what? Because all the vector dot products will give you scalars here. Alright. So we have derived the equations of motion, the three equations of motion in our conventional method, and also in our calculus method, which you have studied in this chapter. Alright. I hope you have enjoyed this session. So in the next session, a little application of this concept we will study. Until then, thank you. Sai Ram.